Wouldn't it be great if we could just store energy? Yes, batteries and things like that. What would this have looked like in the past? Well, who knows? Springs, mechanics, that sort of thing. Lifting weights, the pendulums and things in the grandfather's clock. That sort of thing. Of course, there's a huge limit to the amount of energy that you can store in that way. So there's got to be a better answer. And that's where all this modern electronics comes in. So we're starting with the energy storage being a capacitor. So a capacitor, I've already described it a couple times, but it's basically two metal plates. And these two metal plates are separated by something. Maybe air, but probably not. Probably something non-conductive and insulator. And charges are allowed to build up on here. And in that way, they are stored. They stay isolated and inside of here. Okay, so a capacitor stores. So what do we need? What formulas are we going to need? We're going to need C equals Q. Again, I don't know why I wrote a capital Q, but Q over V. We're going to need our potential is a half QV. Now, what is this? What about this one? We just did this one, and we said this is just QV. What gives right here? Well, this is energy stored, whereas this is change in energy. Okay, slight difference there. I told you, all the formulas for this section would be very confusing. Similar letters and everything. Okay, so capacitance is C, and that's measured in farads. So just a note right there. So that's what we're going to be finding. So C equals Q over V. So C is going to be 27 times 10 to the negative 6 all over 9. And we're going to get a capacitance of 3 times 10 to the negative 6 farad, or just F. Okay, that wasn't so bad. Again, keep a formula sheet. All right, suppose you want to store 5.8 microcoulombs of charge on each plate of a 3.2 microfarad capacitor. Wait, on each plate, you said? Well, yeah, right? You would be storing a positive charge on one plate and a negative charge on the other plate. And they would be identical, although 5.8 positive on one and negative 5.8 on the other. Okay, what is the potential difference of voltage between the two plates? Okay, so we want to store 5.8 microcoulombs. So V equals Q over, what am I talking about? C, talking about capacitance, is Q over V. Now we have a 3.2 microfarad capacitor. So that's 3.2 times 10 to the negative 6 farads equals our charge, 5.8 times 10 to the negative 6 coulombs, all over our voltage. So we'll cross multiply. 3.2 times 10 to the negative 6, V, equals 5.8 times 10 to the negative 6, and then we'll divide. This should be a 2. Divide by 3.2 times 10 to the negative 6. And our voltage, after we divide that out, should be 1.1 or 1.81 volts. Okay, let's go on. What capacitance is necessary to store 9.06 times 10 to the negative coulombs if the potential difference between the plates is 35 volts. Okay, so C equals Q over V. We want to know what capacitance we need for that charge. Well, that's pretty straightforward. Just put it in. Not much to solve right there. And 2.59 times 10 to the, I can't read my writing. I guess that's to the negative 10? I don't know. I guess you'll find out if you're even bothering to check it. Farad. All right, let's go on. Okay, what is the work done? Oh boy, work done. Do you remember work done? Work done equals F times D. But work done is also the change in energy, right? All right, so let's go on. So what is the work done by a 3-volt battery as it charges 7.8 microfarads of a capacitor? So just to talk about that, how can we measure work done by a battery? Work done is things moving. And so let's think about if I had, let's just use magnets. Let's say I had a north magnet and a north magnet, and I wanted to bring them together. Then my work done would be, bringing these close together, and then that'd store up energy. Like I would get these together, and then once they're together, that's stored energy, right? And then they want to pull apart. Okay, so let's go on. That's how we store energy on these things. And so, well, what is the work done going to be? Well, let's go ahead and find this out. So we have a 3-volt battery, and that is set up on a 7.8 microfarad. So I do have a capacitance set up right here. And I want to know the work done. Well, the work done is going to equal the change in potential energy. And we already have a formula for that. The stored energy is going to equal a half QV. Okay, so capacitance. We have 7.8 times 10 to the negative 6 equals Q over 3. We'll multiply both sides by 3, and I get my charge is 2.34 times 10 to the negative 5th coulomb. Now, what am I going to do with that? Well, I'm going to take it over here to my potential energy, and I don't mean this delta. My potential energy is going to be a half QV. So a half 2.34 times 10 to the negative 5th times our voltage, 3. Yeah, I know, we just divided that out, right? And in the end, we get 3.51 times 10 to the negative 5th joules, which we could write as 35 microjoules if we wanted. Okay, that was pretty straightforward, not too much there. A lot of formulas, though. Wow, we have a lot of formulas in this chapter. All right, this is a great problem. I like this one. It is a good one to end on, I think, for the chapter. And that is, you have a 30.31, at least I think that's the last one. We'll see here in a second. But you have a 31 microcoulomb capacitor charged by a 12-volt battery. This capacitor is hooked up to a motor in a 16-kilogram go-kart. Is that heavy? Oh no, it doesn't matter. This thing's not going to go very fast, or at least not in this minimalistic setup that we have here. How fast will the go-kart go if it accelerates from rest, assuming a perfectly efficient circuit? So, what are we going to need here? Well, work done is the potential energy, or the change in the energy there. So let's see. Let's just start writing our formulas down. We have this one. We have this one. This is stored, by the way, this is stored energy. This is the energy on those plates. QV. Okay, why, I guess I didn't really explain why a half, right? But I have two plates, right? So half of the energy is on the left and half on the right. Does that make sense? Well, I hope that's a good explanation. I hope it's the right explanation. That's why I believe it's the case. Okay, so our PE, our potential energy. In order to know that, we need to know the charge. So we have a capacitor, so we have 0.31 farad. We need to know Q, and we are going to have 12 volts, and so we're going to multiply both sides by 12, and we are going to get, and now this should be times 10 to the negative 6 because it's microfarads. So when we multiply by 12, we are going to get 2.72 times 10 to the negative 6 coulombs of charge. Well, that's confusing. C is capacitance, but C is... oh, that's so confusing, isn't it? Here, let's just erase that. All right, so there's our charge. All right, so now we're going to take this and put it into here. All right, so let's do that. So our stored energy is going to be half of our 2.72 times 10 to the negative 6 times our voltage of 12. And we're going to be able to store, when this capacitor is fully charged, 2.232 I lost the unit there. That is unfortunate. I think it's microcoulombs. Guess I'm going to have to type it in again. Give me a second. So 0.5 times 2.72 times 10 to the negative 6 times 12. Apparently I was just making dump numbers here, so I guess I have to redo the whole problem. Make sure all of these are correct. Okay, so this was wrong. This should be a 3 right here, which means this is a 3. And then that gives me this times, good thing I checked, times 10 to the negative 5th. Okay, good. Joules, right? Okay, so here's the idea. So we have that charged on our capacitor, and all of that charge, we're going to say, is used to power the motor. And what is that used for? Well, powering the motor is used to turn the wheels. And what is that used to do? Well, turning the wheels is going to make the thing move. And if it moves, well, then I have kinetic energy. So all of this potential energy is used and converted into kinetic energy because I'm told that I have a perfectly efficient thing going on here. So that means a half mv squared equals my potential energy, which means I have 2.232 times 10. Now, that's not much charge, joules. A half times our 16 kilogram car, which isn't very heavy, I'm not thinking, v squared, and that's not voltage, that's velocity. So I basically have 8v squared equals. So I'm going to divide by 8. And after I divide by 8, I'm going to get v squared equals 2.79 times 10 to the negative 6. And then I'm going to square root that. That's going to have an odd effect, but I'm going to get V equals 1.67 times 10 to the negative third. And that's not voltage, that's velocity, so meters per second. So what's that mean? So our answer, it asks for how fast is it going. And after it's all converted, 1.67 times 10 to the negative third, that's 0.00167 meters per second. You are going to win the race going that fast. All right, hopefully you understood that. It is a lot.